today we have it's my pleasure to introduce you Charis. Charis is Stamatatos. Then he's working in Canada since 2012, something like that. He was working, but because now he's back in Patras. Then he did a PhD in Patras in Greece. And then after he moved first postdoc with George Christou, that is one of the person working in single molecule magnetic clusters in general, with biological interest or also with magnetic interest. And then he was with him several years, and after he came back again to Patras, to Greece, and from Patras he got a position in this university near Niagara Falls. Then where he's enjoying the winters. Then this is a nice place, but too cold place. That's why he's moving to Patras. The Mediterranean part is always much more interesting. Then he has always been working in the field of coordination chemistry and also in coordination chemistry with interests that are in magnetism or also in biological and other kind of applications. But well, today he is going to try to talk not about results on coordination compounds made by organic ligands and metals, but he will use inorganic ligands as metals. For example, like polyisometalates and use oxygen and metal. Instead of using that, he will use some azido, pure azido ligands that are explosive with metals. Well, he will explain us how he stabilized the system in order to make the system not explosive and then make the. Well, if you were to work with him, it is dangerous, you see.
We are dangerous, yes.
Yeah, it's very dangerous because it's comparing things that are quite dangerous. But well, in any case, it seems that so far no students have had any accident with these systems because it's not hitting the compound. Then they don't have any kind of thermal balance. Then somewhere you cannot work there. You like to hit everything, then you cannot work at that place because you will have some explosions. Well, in any case, he will try to develop this kind of new chemistry, and then he will show that it's simple chemistry, but can be useful for preparing some interesting clusters, in that case, magnetic clusters.
Eugenio, thank you very much for the kind introduction and for the kind invitation, and thank you all for attending. Yeah, I'm not going to go through that long, actually, title, which in case any of you is really interested in further exploring, investigating, or reading through this research, you can find that information in the recently published feature article in ChemCom. So that's always as Eugenio said, what we recently tried to establish and develop is a new class of inorganic cluster materials which are purely inorganic, opposite to the traditional cluster compounds in this field, which always includes some organic components. We call those organic bridging ligands or organic chelate ligands. So this is what we try to overcome and see what are the properties, chemical and physicochemical properties of those new materials. If, of course, we were able to manage to crystallize those materials, because these are the challenges when you go above the standard synthetic procedures, which always includes organic ligands. I think I'm going to skip, after that beautiful introduction of Eugenio, that map that I use here always to introduce myself, but maybe we can a little bit go through that. I started from here. I moved through all of these places with different kind of research exchange scholarships, or as the past 6 years as a professor, using the Humboldt Fellowship that I had from the German government. So it was quite an interesting journey all around the world, and now I finally returned back to University of Patras, where I'm going to have the same rank as an associate professor there. So let's skip that map. I don't think it's really interesting to you, and give you a little bit of an idea what my group is actually interested in as an independent researcher the past 6 years or so. So we have several different areas of interest, but this graph here illustrates our synthetic endeavors in the fields of inorganic chemistry and molecular magnetism. So as you probably can see here, what we try to make are those large polynuclear metal complexes using transition metals and lanthanides, or combinations of 3D and 4F metal ions, trying to make those clusters, molecular clusters, as big as possible, because from this you can get valuable information about even the properties of nanoscale, pure nanoscale materials. And we call that the molecular nanoscience, because if you think that a little bit broader, in a broader way, those materials have nano-sized structures and they're still molecules. And this is one of my favorites, actually, favorite compounds. It's a nickel-26 cluster compound with organic ligands all around here, as you can see. And if you use a little bit of your imagination and take most of this organic part out, you see that this is like a rabbit face. And we call that the Bugs Bunny of our lab. And so we were really glad to have that compound, which is not easy to synthesize and crystallize. Now, moving this field a little bit further, when you use the appropriate metal ion, like a manganese, the traditional manganese, which is anisotropic and has also lots of unpaired electrons, and you're lucky, with the right combination of ligands, you stabilize cluster compounds, and hopefully you get nice magnetic properties, and particular single molecule magnetic properties. And this is actually one of the few high nuclearity cluster compounds, actually the highest nuclearity compound with the largest energy barrier reported to the literature today. Moving a little bit further to the lanthanides, the popular lanthanides, then you can start a little bit thinking of smaller systems. It's not anymore necessary to work on high nuclearity compounds, because the lanthanides essentially do not couple strongly to each other, so there is no actually, it's not actually necessary to aggregate those metal ions in polynuclear units. The benefit, the profit from the lanthanide is the single ion anisotropy, which is tremendously large where compared to the 3D metal ions. So you can study new single molecule magnet systems with new properties. And as most of you know, the lanthanides are now at the forefront of research in this field of single molecule magnets and molecular spintronics. And this is our contribution. This is actually one of Eleni's compound. And I think it's the one which still has the record in my group of 110 Kelvin. So the next thing in that actually ranking of compounds is something that we recently tried to develop, the molecular hybrid magnetic materials, molecular compounds, which can include more than one physical properties within the same compound. It's not easy, especially with transition metals, which are known to quench the emission or the photoluminescence properties. Regardless, we have been able to take that magnetic SMM unit, which is a manganese 3 triangle, and change the innocent carboxylates, which do not essentially do anything to the optical properties, with some optically active carboxylates, like pyren, anthracene, fluorine, we have the coumarin, we have the naphthalene derivatives. And what we've actually found out from these compounds is that they still retain their photoluminescence properties. They emit in the red and blue regions of the visible part of the electromagnetic spectrum, while they still retain their SMM properties without changing the SMM dynamics. So the next thing that we would like to try, but we don't have unfortunately the infrastructure, is to see how we can bundle the two properties and see how we can affect one by changing the other. The last thing, still in inorganic chemistry and molecular magnetism fields, is to make molecular magnetic refrigerants, which is something really reasonable. In this case, what we benefit from is the large number of unpaired electrons from the metal ions. We don't care at all about anisotropy in these systems. Actually, we don't want anisotropy. So in this case, we can use those high nuclearity or smaller compounds to cool down other substances. We call those molecular magnetic refrigerants in very, very simple words. So my presentation today will essentially deal with these three parts here, and you will understand, hopefully by the end, you will understand the difference between those materials and the materials that I have already made and all the communities so far in this field. So single molecule magnets, okay, I'm going to be very fast on that. You all know what is a single molecule magnet. Essentially, it's a molecule that upon demagnetization, you can magnetize it. Upon demagnetization, it retains its magnetization. and this is due to a property intrinsic to the molecule and not due to intermolecular interactions from molecules within domains or from domains themselves. The two basic requirements for a molecule to exhibit the SMM behavior is the S, a large bistable spin ground state, which arises from a large number of unpaired electrons in the ground state. The unpaired electrons, in the majority of the case, comes from the metals, unless you work with radicals. And a large magnetic anisotropy, as we call it, the D value, as reflected in a large and negative zero field speeding parameter D. Now, what happens when we have an S and a negative D? So essentially, the S value of the compound splits into two MS plus 1 microstates. And that generates an energy barrier, as you can see here, with opposite orientation of those MS values. So for an S equal to 10, 2 MS plus 1 will be 21 MS states with integers of 1, as you see, going up to 0, opposite direction. Okay, so these are 21 MS states for an S equal to 10 spin ground state. And why I refer to that S equal to 10 spin ground state is because it's the first single molecule magnet which comes from that manganese 12 cluster. So I don't know how familiar you are with molecules, but for sure you know the manganese 12, you know why it has an S equal to 10 spin ground state. It arises through the antiferromagnetic interaction between two different domains of this compound. The outer domain or the outer ring of manganese 3 plus ions, which are ferromagnetically coupled. The ferromagnetically coupled cubane here, but these interactions are antiferromagnetic, so the overall compound can be described as ferrimagnetic, and the S equal to 10 spin ground state. It's a large, but not the maximum for this system. So lots of people were starting thinking why this compound is not the why this compound has an S which is not the maximum one. Definitely because it's quite complicated, correct? Metals in different oxidation states, 3+, 4+, several oxido ligands which are known, antiferromagnetic couplers, carboxylates in the outside. So wherever the system becomes complicated, then this is when you start having competition between ferromagnetic coupling, antiferromagnetic, and what wins at the end is something that remains a question mark. This is why you have to see that from squid magnetometry. Now returning back to the double well here that we can see and the different MS values. So those MS levels, as we call them, the microstates, are separated by that barrier which has a height of U. We call that the energy barrier. Why is it important? It's important from different perspectives because practically and theoretically, or theoretically and practically, you can store magnetic information in any of these levels. So, of course, the magnetization or the spin has to relax. It cannot stay there forever. It takes some time to relax, or it can relax very fast in the majority of the cases. But the three mechanisms for the relaxation of magnetization in 3D, in transition metal single molecule magnets, will be shown here. So the first, and the mechanism that we all would really like to have, is the thermally assisted process where the magnetization goes over all of these microstates and level and relax over the barrier to the magnetization, to the MS state with the opposite sign here. This process gives you the maximum U, which is given by the two formula here for integer and half integer spin systems. This is called the thermally assisted relaxation. Now, if you ask me, is this very rare? It's extremely rare or impossible in transition metal single molecule magnets. That's because the most usual pathway is something that is shown here as a representative example. So the magnetization, as we say, can travel over those MS states. At some point is frozen, or is blocked, as we call it, and then it relaxes through the barrier to the MS states of the resonance structure of the same energy, and down to the ground MS level. This is called the thermally assisted quantum tunneling of magnetization, which includes both thermally assisted and Q2M process. At very now low temperatures, there is a third pathway which is thermally independent. It doesn't depend on the temperature. and this is a pathway that occurs at very low temperatures. This is the so-called pure quantum tunneling of magnetization, or the ground state tunneling, where the magnetization relaxes through the barrier, okay, and that is all. Essentially, you don't get any reasonable or quantified energy barrier for the magnetization reversal. That's my introduction to single molecule magnets. We keep those things in mind because we need the fundamental information to understand some of the phenomena that I'm going to explain to you in a little while. But if you ask me, and of course you know single molecule magnets are not only interesting in fundamental perspectives, there are quite nice applications which have appeared in the literature over the past years from several groups, of course including yours. We can see beautifully how molecules which behave as single molecule magnets can be put, okay, within gold surfaces or in carbon nanotubes. Essentially how you can combine single molecule magnets with properties of the macroscopic world for read and write purposes, okay, for applications in molecular electronics or spintronics. And several other interesting examples to just show and name a few of them. There are quite lots of them in the literature. So it's not only interesting from a fundamental or chemical perspective, but also from quite a lot of applications that we can really explore and develop over the past years. So how about high-spin molecules? That's the title of this slide, to emphasize a little bit our contribution as chemists. So when somebody is a chemist, a synthetic chemist, essentially he likes making molecules. He likes investigating the chemical properties of a compound using synthetic and coordination chemistry protocols. So when somebody comes to my group, the first question is, what should I do? Okay, what should be my contribution to this field, for example? If I ask somebody, okay, go and manipulate the anisotropy, which is one of the two prerequisites, the student is going to be like, so how do I control that, okay? It's really impossible in 3D metals, more particularly, to control the magnetic anisotropy of those compounds. The magnetic anisotropy, essentially, you know, we all know that it's like geometrical characteristics, so it depends on the structure, the symmetry, the topological arrangement of the metal ions, and so on. So it's nothing guaranteed there, and it's nothing that you can really control. What you can actually contribute as a synthetic chemist is to try and see if you can find synthetic routes to maximize, guaranteed synthetic routes, to maximize the spin or the number of unpaired electrons of a molecule, which is something also challenging, but at least it's something that a synthetic chemist can really work on. So my presentation essentially will try to answer one of the questions that the community really tries to find an answer over the past 20 years, if it's a guaranteed control route, okay, or synthetic strategy to high-spin molecules, to molecules with the highest spin ground state possible given the nuclearity and the number of unpaired electrons. So far, the common synthetic strategy that we all follow is the self-assembly. What does that mean? You take a metal precursor, okay, you can oxidize it. If it can get oxidized, you put organic ligands, you do the so-called wet chemistry, and you try to crystallize the most kinetically and thermodynamically stable species out of it. You got the X-ray structure, and you go from there. You see how the molecule looks like, what are all of these characteristics, and you try to predict and, of course, determine their magnetic properties. It's a nice synthetic strategy because although it depends on unpredictability and happenstance, as we call it, it allows you to perform chemical reactivity studies and see how chemically you can manipulate the molecule to bring it into the nice shape in terms of properties that you want like really to get out of it. But still it's not really easy to do something like that. And if you think a little bit as physicists, what we really know is to make two electrons pair parallel to each other or ferromagnetic, it's completely opposite to the nature. This is not what nature really likes. Electrons are half-integer particles or fermions. Okay, they like pairing anti-parallel to each other, so you have to go against nature. You have to flip that electron somehow to make it, okay, ferromagnetic to each other. And we can use the super exchange mechanism, we can search and find ferromagnetic couplers, ligands which are known to bring the two metals or more metal centers, okay, together into a ferromagnetic fashion. And these ligands are azides. They are not uncommon to you, especially in Spanish community, okay? They are not uncommon, and we all know that azides in that end-on ligation mode, bridging 2, 3, or 4 metal centers, only under that, is a guaranteed, essentially, bridging mode to promote ferromagnetic exchange interactions between the metal centers. That's good, that's great. We have ferromagnetic couplers, but azides are the only ferromagnetic couplers. The question is how you are going to make a compound, a high nuclearity compound, where, literally speaking, you need to have not only azides so far, you need to have all of these other components, organic ligands, maybe some oxido, hydroxido, and so on. It's really difficult. And this is actually proved by looking a little bit at the literature. And you find some very interesting compounds which essentially you can say, all right, here we are. Okay, it's already there. We don't need to really develop a new strategy. And as you can see here, those 3 representative examples, these are cluster compounds, lots of metal ions, with tremendously large spin numbers, with tremendously large number of unpaired electrons. However, only those 2 compounds, the manganese 19 of Annie Powell and the manganese 17 of Tassos Tassiopoulos, they have azides, organic ligands, oxido, and still the maximum spin ground state possible for that system. These are super high spin molecules. Excellent. Even that manganese 25 compound of Christou, the first actually giant spin compound, although it has a 51.5 spin ground state, this is not the maximum possible. It's an intermediate spin given the number of manganese 2+, 3+, and the central manganese 4+ ion. If you ask me why is that, it's obviously because we have competition from many different organic components which contribute negatively to the ferromagnetic component, plus other characteristics which arise from the presence of organic ligands. Now, regardless, somebody could say that this is a very successful or a little bit guaranteed route. It could be. But at the same time, looking in the literature, you find compounds like this, which are still high nuclearity compounds. They still have end-on azides, but look at the spin, very low. Antiferromagnetic interactions are predominant on those species, opposite to the interactions here, which means that this is not really a guaranteed route. Okay, because at the same time you can get compounds of large S values, but compounds of very small S values. If you see the synthetic, the blend, okay, as we call it, is the exact same. Metals, azides, organic ligands. In the majority of the case you have also oxides. You get cluster compounds, fantastic, but the spin is not guaranteed. And consequently, the magnetic dynamics are not also guaranteed. And this is where we started a little bit thinking of why that happens. We tried to find the answer by looking at the literature, and we found out that more than 1,000 metal azido clusters with several 300 or more organic ligands have been made so far. In all cases, the only thing that was different was the organic ligand, the organic chelate. The compounds, of course, had different nuclearities, had different magnetic properties, but the synthetic strategy was always the same. And searching a little bit more into the synthetic reactions, all of these products were obtained by using the most commercially available, cheapest, and straightforward azido precursor. You all know that. Let me go to the next. Sodium azide. So that's the precursor that we all know that can deliver azido ions in solution. And this is how all of these compounds were made so far. But if you look a little bit more carefully in those commercial suppliers for chemicals, you can find another guy here, which is called trimethylsilyl azide. And trimethylsilyl azide, in principle, has some fundamental differences than sodium azide. Most importantly, it's more soluble than sodium azide. What does that mean? For us, the synthetic chemists, that means that this allows us to perform reactions in many different solvents, something that is not really the case when you use sodium azide. Good. The second comes from the structure of trimethylsilyl azide. So trimethylsilyl cation here is a cation that is not chemically innocent as the sodium cation. Trimethylsilyl cation has the ability to remove or subtract hydroxides from the reaction solutions. And they form the so-called trimethylsilyl hydroxides. What does that mean? Imagine that as a synthetic, as an environment. The metals are here with lots of hydroxides, so trimethylsilyl azide comes in, takes in principle all of these, the hydroxides, which always compete with azides. Why hydroxides compete with azides? Because they have the same charge, they're also both of them very flexible, and they have the exact same tendency for binding to metal centers. What's the difference, the magnetic difference between hydroxides and azides? Hydroxides are antiferromagnetic couplers, azides are ferromagnetic couplers. So essentially you put a force into the solution which is going to take the hydroxides and leave the metals with azides to try to comply to each other. That was our rationale. So in principle, if that works, the only thing that you really need is trimethylsilyl azide, the metal, and that's all, to make a pure azido-metal complex. But this is not easy at all, because you cannot underestimate the usefulness and necessity of the organic chelate ligand. What's that? The thermodynamic stability. Those organic ligands provide thermodynamic stability to the systems, which make you eventually able to crystallize those compounds. Because we are all, at the end, judged by our ability to grow crystals. That's the only way to evaluate and determine the crystal structure. Good. Of course, this is something that we, as our supervisors, only worry about. Trimethylsilyl azide is at least 10 times more expensive than sodium azide. But I think it was really something that we wanted to try and develop, especially given the fact that in the literature, trimethylsilyl azide in cluster chemistry was only previously used, in this case here, by George Christou quite a long time ago, but not for the purposes of what I'm going to show you. George Christou was trying to make those cubanes with several nu-3 bridging ligands, so he used trimethylsilyl azide in conjunction with different organic components to deliberately, selectively remove this nu-3 ligand, change it from chloride to bromide to azido and so on. A few years after, we took trimethylsilyl azide and we used it as a carboxylate remover. What does that mean? So we used trimethylsilyl azide to make manganese carboxylate clusters, which will have also end-on azides. Fantastic chemistry, we got new cluster compounds, look at them. All of them super small spin states. Essentially, all of them antiferromagnetically coupled. Why is that? Again, for the same reason that we see all of these myriads of compounds in the literature, and they're antiferromagnetically coupled. Carboxylates, oxides, of course some azides. The overall behavior is predominant antiferromagnetic. No guarantee. So, the question here was to try to get this chemistry into a different level, try to remove all of these organic components and see if we can be able to grow crystals of what we really hope to be a new class of inorganic materials. It took us more than 3 years to grow those crystals because the problem was exactly coming from what I've told you before. If you don't have organic component, it's really difficult to grow crystals of a molecular compound. But we figured out what was the key to that challenge, And we were able to make these new classes of pure inorganic materials. They are molecular materials, you can grow crystals, and here we can see two representative structures. It's a cobalt-7 and a nickel-7 isostructural compounds. What we can really see from these compounds and from the reactions shown here is that the compounds have the divalent transition metal ion, which is cobalt and nickel. The cobalt ions are bridged by μ3 and μ2 end-on azides, and there is nothing else. The coordination sites of the metal ions are simply fulfilled by terminal solvate molecules, the acetonitrides. It's a pure nitrogen and carbon-based compound. It's the first cluster which does not have oxygens, transition metal cluster. You can see the side view here, how the azides are displaced above and below the plane. It's like a layer structure. And most importantly was to understand why we were able to crystallize that compound. The reason was the base. So the system needed the base, and it needed the base in order to generate hydroxides in solution. So essentially, the activation of trimethylsilyl azide comes from the previous generation of hydroxides in solution. If you don't have triethylamine, essentially the trimethylsilyl cation which occurs in solution cannot really do anything, and the azides cannot activate the metal centers to bind to each other and form the molecular compound or the crystalline material. So essentially you raise the pH, you generate the hydroxides, you include the trimethylsilyl azide, you remove the hydroxides, and you include the azides into the metal centers. That's the mechanism that we propose for the formation and crystallization of those pieces. We have the structures.
What you have at the end is the trimethylsilyl?
No, here we have the terminal solvate molecules, only acetonitrides. The trimethylsilyl hydroxides are in solution.
And then and why it stops and is not growing in that infinite layer?
That has to do, to my opinion, with the fact that these terminal coordination sites are occupied by solvents. I don't think that this is the only compound. I think it also has to do with the nature of the counter ions here, which essentially block or template the formation of those complexes. So if you give me a little bit of time, I'm going to show you something else where we will understand a little bit better how the aggregation can be stopped or a little bit more controlled. So for us it was important, okay, that we had those two compounds, and if our theory was right, which is not something surprising, we will have what we see here, predominant ferromagnetic exchange interactions in both cases, and the maximum spin ground state for both families of complexes, for the cobalt-7 and nickel-7. So for us it started meaning a little bit that we can start building on something like a guaranteed route to high spin molecules with maximum spin ground states. So in the case of cobalt, we tried to fit, we collaborate with Albert Esquer in Barcelona, and we tried also to feed the data. It was easier here in the nickel-7 because of the lack of that large anisotropy that we have in the cobalt-2 plus ions. We got the J values here, which are both positive. The S equal to 7 spin ground state for the nickel-7 compound, and these can all be confirmed by magnetostructural criteria. If you look at those nitrogen metal angles, they are all below 104 degrees, which is the cut-off, as we say, edge between the ferromagnetic to anti-ferromagnetic switching. Very small angles. So the magnetization data were also collected, from which we were able to determine a large negative D value. So for the case of cobalt-7, we have also SMM behavior, as we can see from this frequency dependence of the AC signals at low temperature, both in the absence and in the presence of a magnetic field. For the nickel-7, we were not actually lucky to have SMM properties at this actually stage. Now, because of this AC maxima here, we can construct a conventional Arrhenius plot, we feed the data to the thermally assisted region, and we get a barrier for the magnetization, reversal, or relaxation of around 28 Kelvin, with a relaxation times within the 10 to the minus 8 second region. So the purpose here is not to really solve a tremendously high energy barrier single molecule magnets, but to try to convince you that this is a nice route, new route to high-speed molecules, giving you the maximum S values. The cobalt-7 and nickel-7 were the first compounds, so we tried really hard to expand this chemistry to other transition metal ions. So the next metal ion that we tried to use was iron. The iron is very, very, how can I say, special, because the chemistry can be different when you work with iron 2+ or with iron 3+, or when you do the reactions under inert atmosphere or at room temperature. And this is where we got two different families of compounds. When we used aerobic conditions, we were able, by starting from iron 2+, to get a mixed valent iron 2+, 3+ compound, which is not actually a molecule, but a two-dimensional coordination polymer. We're going to see the structure in a while. When you use anaerobic conditions, then you can stabilize the iron in the 2+ oxidation state, and then that 2+ oxidation state follows the chemistry of cobalt-2 and nickel-2, and you get an isostructural iron 7 disc-like compound. So let's look at the structures a little bit. So this is the repeating unit of this two-dimensional coordination polymer. It has this bent-like topology. The iron 3+ is here, and these are the iron 2+. It's a mixed valence or valence-trapped compound. If you expand this structure a little bit, you see that this is extended to an iron 6. The iron 6 is then forming those aesthetically pleasing iron 10 cyclic units, and you get then that two-dimensional layer motif by using the entire network and the formalism. The properties are not something like really special. We see long-range ferromagnetic ordering at low temperatures around approximately 35 Kelvin. Above 100 Kelvin, we can still see the ferromagnetic exchange interactions between the metal centers. So it's still the end-on azides promote ferromagnetic interactions. The ferromagnetic ordering was confirmed by doing susceptibility studies at different temperatures as a function of the external magnetic field, and we can see the dependency. We can observe hysteresis loops at temperatures around 30 Kelvin, and the magnetization here corresponds the remnant magnetization to approximately 3.3 electrons and a coercive field of around 0.25 Tesla at 2 Kelvin, the lowest possible temperature. For the iron 7 compound now, which is a molecule, it's a molecular structure. It's exactly the same as the cobalt 7 and nickel 7, and I wouldn't have actually wasted your time here if we haven't seen some interesting magnetic phenomena. In order to understand and explain those interesting magnetic phenomena that we are going to see in a while, I would like a little bit to explain how these molecules are arranged in the crystal. So if you look at this axis and down that axis, you see that the iron-iron separations are quite large. They're around 9 and 8 angstrom respectively. The question is why? Because the clusters are separated by those terminal solvate molecules, the acetonitride molecules. This is what we call the wet sample. The sample which is not dried, where the metal ions retain their solvate molecules, and you can study it as is, the pristine form of the compound. Now, what is the difference between iron 2+ and nickel or cobalt 2+? Is iron 2+, of course, has a significant anisotropy, so you can a little bit look more optimistically into the magnetic dynamics. So we really hope that we had something interesting in there. And before that, we tried to investigate a phenomenon which is called solvation-desolvation effects. Unfortunately, by using only elemental analysis, IR spectroscopy, and some other conventional techniques, because the thermogravimetric studies that we had as an apparatus was not really, how can I say, feasible for us, okay? Or I wouldn't like really want to take the risk to ask a student to do this. and pay him for my entire life if an accident will happen. But the IR was actually really good. What we were actually able to see, just forget those bands here, this is the New York bands from the way that we prepare the sample. We see that the wet compound shown here in red shows all the bands which correspond to the crystal formula of the compound, including the bands here which arise from the acetonitrile molecules. When you leave the crystals in the glove box, exposed, then you slowly see that all of these acetonitrile bands disappear. So something new, something else happens. If you now do the CHN elemental analysis of the dried compound, you get numbers which correspond to the formula shown here. What is this formula? This formula accounts for the unit, the magnetic unit itself, with the counter ion and 2 acetonitrile molecules instead of the 12 plus 4 that you had before in the crystal lattice, 16 in total. Definitely, we see that the exposure of the crystals to the air or whatever, contributes to the removal of those acetonitrile, flexible acetonitrile molecules. So it was good for us because we had 2 samples to magnetically study, the wet and dry. So we started with the dried compound because it's easier to handle and do the conventional squid magnetometry. So the magnetic properties of the dried compound showed something, of course, that we expected. S equal to 14, large chi-MT value at low temperature, arising from the ferromagnetic interactions of 7, S equal to 2, iron 2 plus ions, high speed iron 2 plus ions. The magnetization versus field reduced magnetization studies revealed that this does not reach a saturation, which corresponds to a large magnetic anisotropy, the second important requirement for Nesman behavior, and then we move to the AC dynamics. What is new here? What is actually new is that we see, as you can see in that inset here, 2 thermally assisted relaxation processes at 2 different temperatures. Those 2 relaxation processes do not overlap with each other, as we usually see in lanthanides. And as you see, they have actually the same intensities. So that means that in the dried compound, something is going on, different than what has been seen so far in these transition metal cluster SMMs. Things like that has only been previously seen in the Young-Teller isomerism effect of the manganese 12 approximately 20 years ago. So, if you take those 2 processes, you feed the data easily, then you construct Arrhenius plots and you get 2 different energy barriers for the low temperature, for the magnetization reversal. The high temperature and the low temperature. Of course, a wide variety of different studies can be done. You can fit those data by Debye equations and so on. We also explored and calculated the phi to exclude spin glass behavior. Definitely it's not the compound a spin glass. And of course, you have 2 ways. Either you sit down and you try to understand what is going on with the dried compound, and you stay there for months or years trying to understand, or you go to the wet compound, you put your crystals in an NMR tube, you stick it in the squid, and you see if you get the same behavior or not. That is going to be very helpful to understand the phenomenon and the difference between the 2. And this is what we got from the wet compound. In the wet compound, we see the same chi-MT as before. The ground state, of course, remains the same. Nothing has changed. The azides are there. They contribute to the ferromagnetic coupling. The magnetization is the same, but only the low temperature relaxation. We only see 1 relaxation below around 3 Kelvin, which is the low temperature one. We don't see the high temperature relaxation. So that, with the current state of our studies, allowed us to get some tentative conclusions. So what we really believe, excuse me, I forgot to mention that this has a 14 Kelvin energy barrier, but this is not the important part here, is to understand and explain what's going on. So we believe that we have a large contribution of the intermolecular interactions which contribute to the onset of the high temperature energy barrier. We believe that in the dried compound, those acetonitrile molecules are completely removed. Then the molecules get closer to each other, and you start having interactions between the clusters within the crystal lattice. So that's option number one. Option number two, it's not impossible that upon drying and removal of those acetonitriles, some of these tails of azides become bridged with real bonds, and that bridge connects those clusters in the crystal. In this case, then you expect to have something like SMN from the cluster and single chain magnet between the clusters, which could explain the two different relaxation processes. Keep in mind, these are all scenarios. We don't have so much data at this point, but we would like to investigate those further. Now, a third scenario comes from maybe the difference in the magnetic anisotropy. If you have two relaxation processes, but at different temperature, provided that the molecule is the same and the spin is the same, then the only way to explain the difference, okay, one of the ways to explain the difference will be what? By changing the D, the magnetic anisotropy. Provided that we don't have here acetonitrile molecules within the metal ions, then you get the structure in the dried compound of that kind. Now the metal centers here, the outer metal centers, are not anymore 6 coordinate, they are 4 coordinate. And you use the SAVE program to calculate the continuous shape measures. In a hypothetical structure, I don't have a crystal structure of the dried compound because the crystals do not diffract in the dried form. But in that hypothetical structure, if you perform SAVE calculations, you find out that the iron centers have a seesaw geometry. It was Jeffrey Long 2 years ago who published a paper saying that the iron 2+ centers, single iron magnets, with a seesaw geometry has an order of magnitude larger magnetic anisotropy than the octahedron. So that could be another hypothetical reason why the dried compound shows that second higher temperature relaxation process. So all of these solvation-desolvation effects are quite exciting and to me, and quite rare, and I would really like to have more, okay, to show you. We'll see in a while if we have any. But for us, as you know, Eugenio pointed before, was also chemically important to see how we can overcome that stability of the heptanuclear compounds. Do you know how many students came in my group and I saw them this project and they said, and what I'm going to do, another heptanuclear compound, I'm really bored. You have already made quite a few, so we want to try new things. We want to expand the nuclearities and see if we can get something different, which was really difficult and really challenging. So we decided to go with that, what we call the beauty of chemical reactivity, and understand chemically what is the reason that these compounds are stable heptanuclear disk-like units. The only thing that we could think of is the counterion. The perchlorate counterions which stabilize those heptanuclear units. So I asked my student, in collaboration with German partners, due to the Humboldt fellowship that I have, to try and replace those perchlorates with a larger or smaller counterions. And we figure out that when you use lanthanide nitrate salts, the very common lanthanide nitrate 5, 2- counterion, you are able to template the formation of 2 fused heptanuclear units and get that decanuclear, new class of decanuclear nickel-10 compounds, again with that layer, beautiful layer structure here, and the lanthanide nitrates are just acting as counter ions. This is the core, the metal topology. Again, we have only bridging azides. The terminal sites here are occupied by terminal acetonitride molecules. We still see here solvation-desolvation effects. You see that the crystals change at room temperature. Thanks God we don't need to put those crystals under glad box because nickel cannot get oxidized. It's always stable in the 2+ oxidation state. And we were able to figure out how the crystal degrade with time. So 10 nickels, a guaranteed route to high-speed molecules. If that's the case, that should be S equal to 10. So all of these nickel 10 compounds, they have S equal to 10 spin ground state. Of course, the overall number of unpaired electrons depends also on the unpaired electrons of the counter ion. We don't have SMM behavior, but we really have interesting magnetocaloric properties here, which is something that we haven't published yet. These are very recent results. We were not able, because they are not single molecule magnets, to see dynamics as we saw before with the iron 7, the two processes which could rely on solvation-desolvation effects. So we were not very liking this case here. So in conclusion, we saw, I'm not going to go through all of this, we saw a variety of different compounds which to our opinion demonstrate the usefulness of that synthetic approach, which I would like to call it a guaranteed synthetic approach to high-speed molecules and potentially to molecules with quite different or rare SMM properties, like the two relaxation processes that we saw before. Of course, what my father taught me is that one example is never enough. You always need to have two in order to demonstrate something. And therefore, I think that this example here, as the final before I finish my presentation, could really demonstrate the fact that we can have solvation-desolvation effects in clustered compounds. It's a nickel 18 compound. In this case, it doesn't only include azide ligands, but also peroxo ligands. First process at around 20 Kelvin with a barrier of 400 Kelvin, by far the largest barrier in 3D metal cluster SMMs. It's an unpublished result. It's the first time that I show it to the community. And the second relaxation here, which is more intrinsic to the molecule itself. Wolfgang Verstofer has done the single crystal hysteresis studies, but at low temperatures. And he was able to find out that this molecule is a single molecule magnet here. And, excuse me, at high temperature, this is just a first result. Okay, we try to find collaborators and see what we can do. We want to study the wet and dried compound. This is a dried compound, I forgot to mention. So I would like to finish by thanking all of you for your attendance. I hope you enjoyed. I hope you understood a little bit this class of new inorganic, pure inorganic molecular materials. And thank you all.